This is the homework assignment for lesson 1-3 in the textbook, numbers 1 through 19. So number 1, consider the sequence created by the square tiles shown below. We're going to evaluate this expression for various values of n, so we're going to specifically choose these. That describes the number of squares in the nth term. So we have this nth, and that just represents what term. So n is the variable that represents the term number. This is term 1, term 2, term 3. So n, or the term, is 1, 2, or 3. We want to know, does this expression represent how many tiles there are in any term number? So when they say the nth term, they're just talking about the term number, 1, 2, 3, all the way up to 100 that we'll look at in part B, or any number. So part A, we're going to look at the first, second, and third term. So we're plugging in for n. So 3 times 1 minus 2, so term 1. Well, 3 times 1 is 3 minus 2 is 1. So that works. This expression, if you plug in term 1, gives you the value of 1, and that's how many tiles we have here. So let's test it for 2. If I plug in 2 to this expression, 3 times 2 minus 2, that's 6 minus 2, and that's 4. And if I count the tiles, I've got 4 tiles. So far so good. This expression represents the number of tiles when you plug in the term number. Let's plug in term 3. So it's going to be 9 minus 2, which is 7. And if you count them up, 1, 2, 3, 4, 5, 6, 7. So this appears to work. This expression appears to represent the number of tiles in the nth term, whatever term we are looking at. So part B, now go ahead and use the expression to find the number of tiles in the 100th term. So all you're doing is plugging in 100 now for the term, which is n. And so it's 300 minus the 2. So there would be 298 tiles in the 100th term. Okay, question 2. Consider this sequence of dots. So as we look at it, we've got 4. Then we have 1, 2, 3, 4, 5 up with one more row added, or column added. Then we go 6 up. So we're going up by 1 every single time. So 4, and then 5, and then 6, plus adding a row. Now, how many rows, if you notice, matches the term? Term 1 has 1 row. Term 2 has 2 rows. Okay, now we need to try and figure something out for this 4, 5, 6. So looking at part A, draw the 4th and 5th terms. Write the multiplication expression for the number of dots. So you can see that's located right there. So the 4th term is going to have 4 rows. 1, 2, 3, 4. And if you're just following this progression, 4, 5, 6, there should be 7. 2, 3, 4, 5, 6. 7 down. Okay, so you take a look. We have 4 rows here, and there's 7 across, so 7 times 4, so 28 dots. And term 5, so this is term 4. Term 5, we're going to have 5 rows across. And now we're adding one more down, so there'd be 8. So 1, 2, 3, 4, 5, 6, 7, 8. I don't know if I missed the dot, but we get the point. So there's 8 times 5, and that's 40. So letter B, in words, describe how to find the number of dots in the nth term if you knew the term number. So as we start to look at this, you could say, okay, I know it's the term number, right? Here's the 5, here's the 4, 3, 2, 1, times something. So times 4, times 5, times 6. We have to find some kind of pattern. Well, if you look at those numbers, they're always 3 apart. And that's something that you just have to analyze and start to see. So the 4 and the 1 are 3 apart, the 5 and the 2 are 3 apart. So you're taking the term number, and multiplying it by what? So term 5, multiplying it by the number that's 3 more than it. Term 4, multiplying the number that's 3 more than it. So multiply by 3 more than the term. And then part C, let's take this now and write an expression that represents this. So we want to take the words that we just used, so multiply the term number, so n, times the number that's 3 more than n. So you're going to take n and you're going to add 3. So whatever the term is, add 3 to it, multiply that by the term. Now, we have to put this in parentheses because order of operations says that if I don't, you're going to multiply first and then add 3. And that's not what we're doing here. Okay, we're adding 3 to the number and then multiplying it by that. So it looks like this. All right, number 3. So we have 2 different expressions to generate each table. We're going to use the tables to decide whether they are equivalent. So this is one way to test equivalence. Is this expression equivalent to this? You could also simplify this and see if it becomes this expression, and that would also show if they're equivalent. But we can just test numbers, and we should produce the same values. This is also called inputs and outputs. If we have the similar input and they produce the same output, okay, then we can see that they are equivalent. So just redrawing these tables here, 10, 9, 8, 7, 6, 5, for 3x minus 17. So we're just plugging these numbers in. You don't have to show your work here. 3 times 10 is 30, minus 17 is 13. 3 times 9 is 27, minus 17 is 10. 3 times 8 is 24, minus 17 is 7. 3 times 7 is 21, minus 17 is 4. 6 times 3 is 18, minus 17 is 1. 3 times 5 is 15, minus 17 is negative 2. So we're going to do the same thing now. It's a little more complicated with this bigger expression. Still plugging in 10, 9, 8, 7, 6, 5. So similar inputs, and we're going to see are our outputs also similar or equivalent. Okay, so if we were going to run this out, we're going to take 10, we're going to do parentheses first. So 2 times 10, that's 20. 11 minus 20, that's negative 9. And this would also be 10. So you would do 10 minus 6, which is 4, minus negative 9. When you minus a negative, it goes plus plus. And you could run this all through your calculator. You do get 13. I don't want you to get lost in just the math up here. Okay, the important part is understanding what we're doing. We're testing to see if they're equivalent. You plug in 9. 2 times 9 is 18. 11 minus 18 would be negative 7. Over here you'd have 9 minus 6, that's 3. 3 minus negative 7 goes plus plus. 3 plus 7 is 10. And then you can see they're similar so far, and sure enough, if you run the numbers, I don't want to waste too much time on just plug and chug, you would get the same. And so explain how you know. I would say yes, the expressions are equivalent. And your explanation here is just as important as all of your work. Yes, the expressions are equivalent. Use those good vocabulary words. Because, and here's where you want to use some nice math language. Similar inputs, those are the numbers that you're plugging in, you're inputting them. Similar inputs produce similar outputs. That makes you sound really smart. Similar inputs produce similar outputs. Okay, moving on, number 4. All right, so consider this sequence of toothpicks shown at the right. A student describes those, blah, blah, blah. I split the toothpicks into 3 kinds, kind of just going through explaining how they came up with an expression. So in the nth figure, there were n toothpicks on top, blah, blah, blah. So this is one of those ones where we have to kind of weed through this. Let's go straight to the question. It says substitute for n to verify that this expression describes the number of toothpicks needed. So test it. Basically, they explain this person came up with this expression. It's kind of complicated, but does it work? So we're going to plug in the terms, the 1, 2, and the 3. into their expression that they say works, and we're just going to test it. Okay, so our expression is n plus in parentheses n plus 1. So let's test term 1. If we plug in 1 plus 1 plus 1 plus 1, we're going to get 2 here. We're going to add it all up. That's 4. Do we have 4 toothpicks in term 1? Yes. So that one works. Term 2, plugging 2 in everywhere we see an n. So 2 plus 2. In here, it's n plus 1, so 2 plus 1. I'm going to get 3. So 2 plus 2 is 4, plus 3 is 7. Count the toothpicks. At first you might think there's 8, but we have 4 right here and then 3 attached onto the end. So 7 is true. In term 3, again plugging in for n, 3 plus n plus 1, 3 plus 1, that's 4. So 3 plus 3 is 6, plus 4 is 10, and if you count it up, we've got 4, 5, 6, 7, 8, 9, 10. That works. So for part A, we've proven that even though this looks a little crazy and it's not simplified, that this expression does produce the number of toothpicks in each term. So we can go ahead and use this now, part B, to find out how many toothpicks there would be in the 100th term of this, rather than trying to draw that out. So plugging in for n, plugging 100 in, it's 100 plus 100 plus 100 plus 1. Well, this would be 101. So 100, 200, 300, and 1. Okay, moving on to number 5. So these are similar to what we did up here on number 3. They just don't kind of show it to you the same way, but they're asking you to do the same thing. So using a table, that's what these are, using a table. Evaluate each expression for 4 different values. So we're going to test these two, so separate, kind of like this. Based on your results, tell me if they're equivalent. So I'm going to make one big table. You can make multiple tables. So here's how I'm going to set it up. You don't have to do it this way. So I'm going to put this expression, 25 plus x minus 5 times x plus 5. In my table, I'm also going to put x squared in my table, and I'm going to plug in numbers for x. So these are the numbers I'm plugging in right here. I'm going to go 0, 1, 2, and 3. It says 4 numbers, so there's my 4 numbers I'm going to plug in. So let's run through the x squared first. That's easy. Plug in 0, 0 squared is 0. Plug in 1, 1 squared is 1. Plug in 2, 2 squared is 4. Plug in 3, 3 squared is 9. So basically, I'm going to plug these numbers now into this expression and see do similar outputs. Are similar outputs produced from the similar inputs? So let's start with 0. 0 minus 5 is negative 5. 0 plus 5 is positive 5. Following order of operations, multiplication before I add. So negative 5 times 5. It's negative 25. 25 plus negative 25 is 0. Again, if you can't do this in your head, use your calculator. Plugging in 1. 1 minus 5 is negative 4. 1 plus 5 is 6. Multiply those together, that's negative 24. 25 plus negative 24 is 1. And I'll save you the time. These do come out like this. Based on your results, are they equivalent? Yes, and if it asks for an explanation, you would say similar inputs produce the same outputs. Oop, and I was going too fast here. I wrote down the wrong numbers here. Okay, so 2 squared was 4, 3 squared was 9, and these, when you plugged them in, also gave you 4 and 9. Sorry about that. Okay. Going on to number 6, we're going to run through this the same way. So we're going to make a table. These are the x values I'm plugging in. Again, I'm going to go with 0, 1, 2, and 3. Just keep it simple. My expressions are 8n minus 4 over 4 and 8n minus 1. So plugging in 0, 8 times 0 is 0 minus 1 is negative 1. 8 times 1 is 8 minus 1 is 7. 2 times 8 is 16 minus 1 is 15. 3 times 8 is 24 minus 1 is 23. Plug in 0. 0 minus 4 is negative 4. Divided by 4 is negative 1. Okay, looks good. Plug in 1. 8 times 1 is 8 minus 4 is 4. Divided by 4 is 1. Well, all of a sudden, look, it looked good on the first line, not good here. Now, technically, you could stop right there. These are not equivalent. But let's make sure we didn't make an error here. Let's plug in one more number and make sure that it's not working. So 8 times 2, that's 16, minus 4 is 12, and 12 divided by 4 is 3. And you could go one more step. 3 times 8 is 24, minus 4 is 21. Oh, what did I do here? Oh, I'm sorry. 8 times 3 is 24, minus 4 is 20, divided by 4 is 5. So we could have stopped up here as soon as we saw it was not equivalent. Our answer here is no, not equivalent. Similar inputs to these expressions produce different outputs. So no good there. And number 7. Same idea. Plugging into both, I'm again going to just go ahead and do 0, 1, 2, and 3 and plug in. Now, I'm just going to save the talking through each specific one, but when I plugged in 0 to this one, you can see you're going to get 0 squared is 0. 4 times 0 is 0. So 0 and 0 minus 3 is negative 3. Over here, you end up with 0 plus 1 is 1. 0 minus 3 is negative 3. You multiply, you get negative 3. So just like here, we end up with the same output for 0. But when you go ahead to 1, you end up with a negative 6, a negative 7, a negative 6 when you plug those in. This is just, I've done this previously. And then you plug these numbers in, and you get a negative 4, you get a negative 3, and you get a 0. So you can see they do not match. So to answer part B, based on your results, do they appear to be equivalent? And you would say no. And again, if they asked you to explain, you say similar inputs produce different outputs. All right, slide over to number 8. Now actually trying to come up with these expressions for this. It can be a little tricky, but there is a process, and if you follow the process, it works every time. All right, so we have these tiles here, letter A. Write an expression describing the number of green. So in term 1, there's 1, in term 2, there's 2, and in term 3, there's 3. So the number of green tiles just is the term number. 1, 2, 3. There's 1, there's 2, there's 3. So whatever n is, the term number, that's the number of tiles. So write the expression describing the number of green tiles in the nth term. So it's just n. Whatever the term number is, that's how many there are. All right, here's the tricky one. Write the expression describing the number of yellow tiles. So I'm going to walk you through this process. We are going to make a quick little chart here. So we're going to take the term number, and we're going to write the number of tiles, and we have to find a pattern. And then we're going to write the expression for that pattern. So we have term 1, 2, and 3, going directly from here. So in term 1, how many yellow tiles do we have? There's 6. In term 2, you've got your 6 plus another 4. That's 10. That plus 4 is important. So if you look, here's our 2 circles. How many have they added on the next one? Another 4 here on the outside. If you knock those 4 off, you've got the same picture as number 2. So they've added 4. We've got 14. The adding 4 is important. They're adding 4. That is called your rate of change. It's increasing by 4, and eventually we'll talk about slope of a line. That is the rate of change. And so when you go ahead and you write an expression, the rate of change is what is going to be attached to your n, or your variable. So I'm going to start off by writing 4n. So whatever the increase is for every single term, that's the coefficient or the number that gets attached to n. Now, usually there's going to be a plus or a minus. And so what you want to do is you want to go ahead and test what we've got so far. And if it's not producing the right amount of tiles, figure out how far off is it for each term. It should be the same amount. And then we make the adjustment, either a plus or a minus. So if I plugged in 1, 4 times 1 would give me 8. So I'm off by 2, right? I'm too high right now. This expression does not work. I got 8, should have got 6. If I plug in 2, gosh, I'm getting ahead of myself. You're probably thinking, how in the world did he get 8? Plugging in 1, 4 times 1 is 4. I'm low by 2. When you plug in 2, you get 8. I'm low by 2. You plug in 3, 4 times 3 is 12. I'm low by 2. So you can see right now this expression doesn't work, but It's only off by 2. So the answer that I get when I plug in the term needs 2 added to it to get the number of tiles. So I'm just going to go ahead and add that to the expression. This will now work for every single term. So again, one more time, how did I get that? So first, just count the number of tiles, compare it to the number of terms. See what it's increasing by. Going up by 4 in this case, that's your rate of change. That's the number that gets attached to n. And then I test my initial expression, which is just for n. Plug in the term numbers, see what I get. And it should be the same amount off for every single one. And then you make the adjustment. I need to add 2 to every answer that I got to actually produce the number of tiles. So there you go. Okay, part C, use your answers from parts A and B to write an expression describing the total number of hexagonal tiles in the nth term of the sequence. The total number of tiles. So this is the number of green tiles, and this is the number of yellow tiles, or whatever color you want to call that. So if I wanted the total number of tiles in 3, it's the number of yellow tiles, plus you got to add those 3 green tiles, which would be the n. So basically, if I want to know what's the total number of tiles in a term, I'm going to add the green, and I'm going to add the yellow. I'm going to write that out so you can understand it. I'm taking the green, I'm adding the yellow. This tells me how many green, this tells me how many yellow. So I'm actually adding these two together, n plus 4n plus 2. Now, you could go ahead and you can combine that. You could simplify this. We should know how to do that. N plus 4n is 5n, and the plus 2 stays separate. So either one of these work. This is good, it's just not simplified, and this is good, it is simplified, but they're equivalent. It says the same thing. Okay, these are equivalent. So letter D, how many hexagonal tiles are in the 100th term? If I plugged it right in here, 5 times 100 plus 2, I'd get 502. So that's the correct answer. But I want you to see, you could also plug it in here. You're going to get 100 for when you plug it in for n, plus 4 times 100. Remember I told you about my handwriting? Plus 2. Well, 4 times 100 is 400. Put that together, that's 500 plus 2. You get the same answer. So that's important. I need you to see that. These are the same. They're equivalent. One is just simplified and is easier to use. So if you can simplify, it's worth it. But these are the same thing. So we added the green tiles, which is represented by n. The green have the same amount as the term number. We added it to the yellow, which we went through that process to find out what's the expression that represents the yellow, and then you just add them all together. All right, that's a lot right there. Going on to number 9. Give a counterexample to show that this equation is not true for all real numbers. So we've got a minus b plus b equal to a minus 5 plus b. So a counterexample is something that shows it is not true. So we got to come up with something that when we plug in for a and b, these two sides of the equation are not equal. Right now it's saying if I can plug in any number I want for a and b, so a equals 1 and b equals 2, plug them in, this is going to equal this. So we need to come up with a counterexample. So let's try a equals 5 and b equals 0. Okay, if I go ahead and plug that in, 5 goes in here, 0 goes in here, plus b, that's 0. And then on this side, a is 5. Inside parentheses, 5 plus b, which is 0. So I get 5 inside parentheses plus 0 is 5. On the other side, 5 plus 0 over here, I get 5, and 5 minus 5 is 0. I feel like I made a mistake here. Let's see. A minus 5. Oh, I just copied it wrong. So the original here has a 5 here, not a b. So this should be a 5, which would produce a 0. And 0 plus 0 is 0. Okay, so just a silly error there from copying that. But I knew from previous work that these two actually would prove this is true. So this is not a counterexample. So it's important to see that When I plugged in the 5 and the 0, even though I made a mistake, once I've corrected it, both sides came out to be 0. So that means that right now this proves that this is true. So we need a counterexample. So here's what I want you to do. Plug in positive numbers, maybe even a 0, and see if it works. If it does, that doesn't necessarily mean this is always true. So plug in something else, like a negative number. So I'm going to plug in -1. And then anything you want over here, let's go with 6, since that's what I've got on the key. So I'm going to go ahead and plug those in. So it's a minus 5, so that's -1 minus 5, plus b, so plus 6, on that side of the equal sign. On the other side, I've got a, so -1, minus 5 plus b, so 5 plus 6. Run these out. I get -6 in here, and I get 11 in here. -6 plus 6 gives me 0. And over here, -1 minus 11 is -12. 0 does not equal -12. Okay, so this does not work. This is a counter example. That's really what this question is testing you. Do you know what a counter example is? Find some numbers that prove that this equation does not always work. There are situations where it is not true. Okay, number 10. An airplane manufacturer sells small planes that have seats arranged like this. In each row, there are 3 seats on the left, 2 on the right. If there are r rows of seats, find 2 different expressions here to represent the total number of seats on the plane. So every row has how many? Forget the fact that it's split up into 3 and 2. Every row has 5. If there was 1 row, you'd have 5 seats. If there's 2 rows, you have 10 seats. If there's 3 rows, 15. So there's 5 seats in every single row. So 5 times the number of rows gives you the number of seats. How else could you do it? Well, you've got 3 and 2, right? So 3, you could figure out how many are in this section. Well, if there was 2 rows, you'd have 6. And then over here, you'd have 2 times the number of rows. So you'd have 4, or if it was just 1, you'd have 2 and 3. And these would get added together. So it's just another way of writing it up, but 5r makes the most sense. If you simplify this, 3r plus 2r is 5r. So it's just coming up with a different way to think about it. But if you plugged in, let's say we've got 4 here. You plug in 4, we're going to get 20. There's 20 here. If you plugged it in here, 4 times 3r would tell you how many seats are on this side, and 4 times 2r would tell you how many are on this side. And then you would add them together, and sure enough, you would also get 20. Okay, so I don't want to focus too much on that. Just noticing that we can write an expression based on the number of rows. Okay, number 11. Describe the general pattern using one variable. So you can use any variable you want when you do these types of problems. Just trying to figure out what is constant and what is changing. So as I look at this, I see the 1 appears in every single one. It's the only number I see that's constant besides the exponent. Everything else here is changing. And it's an 8 every time, and then it's a 30 every time, and then it's a 6.5 every time. That's the variable. That's what we're plugging into. We plugged in for it with an 8. We plugged in for the variable with a 30. We plugged in for the variable. So when I write this expression, I know my variable is here. I know my variable is here. I know my variable is here. And I know it's right here. But the -1 is part of my expression. Okay, that is not replaced by the same number as everything else, so that has to stay. Okay, number 12. Each morning, Crystal buys a cup of coffee for $2.25. She uses a table to record her total expenditures. So day 1, it's $2.25 because that's how much for 1. Then after day 2, she's had it twice. So she shows it with addition, right? Same thing for day 3. You could use multiplication, 3 times $2.25, 2 times $2.25, instead of adding it. So if you finish this table out, okay, day 4 and day 5. So day 4, you would have $2.25 4 times. And day 5, you would have it 5 times. A little tedious here. And then your total cost. So you could just multiply. So we're going to go 225 times 4. That's 9. And then 225 times 5. It's 1125. After 1 year, how much will she have spent on coffee? Well, 1 year is 365 days. Of course, it could be a leap year, but whenever they ask you that question, they're just looking for a standard year. So times 225. So 365 times 225. $821.25. Now they want you to write an expression after d days, so meaning any number of days. Explain as an expression pretty much. How do you know how much it costs? So you take the number of days, which we're going to represent with a d, and you times it by the cost of a cup of coffee, which is 2.25. Now, we want to simplify this. We always rewrite with the coefficient up front. So the way you would really write it is 225d, but these say the same thing. You're taking the number of days and multiplying by $2.25. All right. 13, give 2 instances of each pattern. That just means you're plugging in any number that you want. You don't have to fully solve out an instance. You just plug something in. So I've got x squared times x equals x to the third. One instance of that would be plugging in the number 4. 4 squared times 4 equals 4 to the third. I just chose a random number. Plug in 0. 0 squared times 0 equals 0 to the third. You don't have to finish those out unless it tells you to. Those are just instances, just random things you're plugging in. So for b, it's 3g minus g equals g. Plug it in. Anything you want. I'm going to plug in a 2. Now you could test that instance and make sure that this comes out equal, but they're not asking you to do that right now. They're just asking you to come up with an instance, which just means plug in a number. So for letter C, looks like this. Plug in anything you want. I'm going to plug in a 1. Now 3 plus 8 stays. You're only plugging in for n. And that's it. And then let's plug in a 2. There we go. All right, that's 13. So when they ask you to come up with instances, that's all they're asking for. Sometimes we get confused. We think there's something else we have to do. That's it. All right, 14, we're going to evaluate this when x equals 200. So 1 over 10 times x squared. So 200 squared. First thing I'm going to do is exponents. So 200 squared, you can run that in your calculator, is 40,000. That has to get times by 1/10. Now how do I do that? You can use your fraction button. So you do 1/10, ABC button, times 40,000. That gives you your answer. It's 4,000. The other way you could do it is turn it to a decimal. 1 divided by 10 is 0.1. So 1/10 is equivalent to 0.1. Just divide. It gives you the decimal version. Times 40,000. And I get the same answer there. Okay, part B. We're going to change it up a little bit and put parentheses here. So that changes the order that I have to do things. So 1/10 times 200 squared. So first thing I'm going to do is 1/10 times 200. So 0.1 times 200 is 20. And 20 squared, 20 times 20 is 400. So you notice different answers. So they changed the parentheses. We got a different answer. Part C, we're going to go ahead and find a value where if we plug it into these two, we actually do get the same number. So if you just saw 200, a positive number, get plugged in, and you got to find one that is going to give you a different result. Look at a 0 or look at a negative. Okay, positives, 0, and negatives tend to show you the clear differences when we have an expression, if there is one. So if we go ahead and plug in 0 for x, so when x equals 0, for the first one, it's going to be 1/10 times 0 squared, which is just 0. Multiply here, we get 0. And what about the other one? So in parentheses, 1/10 times 0 squared. Well, 1/10 times 0 is 0. Squared is 0. So we get the same value for both, even though we know that these are not equivalent. We plugged in 200, we got different answers. We plugged in 0, we got the same answer. So these are not equivalent, but that doesn't mean there aren't instances where they show or give you the same output. Okay, 15. Fill in the blank with an equals, a less than, or a greater than. So we don't even have to do the math here. We just want to make sure we understand our positives and our negatives. That's really what we're looking at here. When you multiply two negatives, this is going to get me a positive number. When I add two negatives together, I get a negative number. So regardless of what the actual answer is, a positive will always be bigger than a negative, and so this is greater than. 16. 3 to the third plus 3 to the third is what compared to 3 to the sixth? So this one, you might want to run the numbers. 3, here's my raised to button. Kind of hard to see there. 3 raised to the third is going to look like this. Raised to is that little arrow pointing up. Hit equals, it's 27. So I'm going to get 27 plus 27, which is 54. And how does that compare to 3 raised to the sixth? So 3 raised to the sixth looks like this. And I get 729. So clearly these are not the same. So 3 to the third plus 3 to the third is not 3 to the sixth. Okay, they are different. Okay, this is bigger. You're going to get 729. Okay, 17. We've got 8 times 6 times 3 plus 1 equals, and then they just changed the parentheses here. So it's 8 times 6 times 3 plus 1. So here you would multiply first because it's in parentheses, then multiply, then add. Here you would do the parentheses first, you'd multiply, and then add. So this is showing you the commutative property. We're changing the order in which we multiply. It's also the associative property because we are changing the grouping here. But if I did 8 times 6, then times 3, and add 1, you're going to get 145. Over here, I'd have to multiply the 6 times 3 first. Get 18 times 8. I get the same number, plus 1, get 145. So these would be equal. So what we want to recognize is that even if we multiply in a different order, commutative property says we're still going to get the same answer. So whether I do 8 times 6, then times 3, or 6 times 3, and then times 8, they will produce the same answer. That's the commutative property, going back to that which we studied last section. Okay, 2 more to go here. 18. So the video store has DVDs on sale for $9.95. All others are $14.95. So a customer wants to purchase 7 DVDs, 2 of which are on sale. What's the total cost? So 2 are on sale. So 2 of them are $9.95, which means 5 of them are $14.95. You'd multiply, and then you'd add up your total cost, and that's $94.65. Okay, and 19. LA charges a sales tax of 8.25%. So first of all, 8.25%. We got to turn that to a decimal. We move it 2 to the left. It's 0.08. That's 8%. And then you tag on the 2, 5. You just continue it on. So this is the decimal version of it. If you have 20%, decimals here, you move it 2 spots. That becomes 0.20 or 0.2. So if you want to find 20% of something, you multiply by 0.2. 8%, here's the decimal, move it 2 spots. It's 0.08. So 8.25%, the 8 is the 0.08, and then the 2.5 just gets tacked on. So you bought a pair of jeans that cost $35 before tax. What's the total cost after tax? So first of all, you're going to pay the $35, right? That's the cost. But you also have to pay the tax on top of it. So we're going to add something to 35. We're going to add the tax. we need to find what's 8.25% of 35. So anytime you want to find the percent of something, you just take the number and you multiply by the decimal version. So 0.0825. That'll tell you what is 8.25% of 35. So we're going to go ahead and multiply that. So 35 times 0.0825 looks like this. So I'm going to have 35 plus, now I'm going to round this up, 89 cents. So when I go ahead and add these together, I'm going to get $37.89.